What's up, guys? It's Mr. Brengle, and today I'm going to be going over the math problems for pendulums. So if we'll take a look right here initially, this is the equation for the period of a pendulum. I usually write it as T subscript P for pendulum because there's also an equation for the period for a spring, and they're very similar. So the period of a pendulum is equal to 2 pi times the length of the string divided by the acceleration due to gravity, and all of that is under a square root. Okay, so I want you to think about this for a second. We've already done the pendulum lab and we tested how does mass affect the period of a pendulum. It didn't. How does the angle that you release at or the amplitude affect the period of a pendulum? It does not. And then we tested the length, and the length did affect the period of a pendulum. Well, you can see that the length is in the equation here for the period of a pendulum. And then also the acceleration due to gravity, which remember, g is equal to 10 meters per second squared in our class. So this kind of helps us understand the results of that lab that we did. The length of the string matters, and then obviously when you drop an object, it starts accelerating. Every object accelerates at the same rate, so the mass doesn't affect it. Now let's say I have a pendulum, and we're going to make this one really long here, and there's something hanging on to it, and let's say it goes out to this angle here, and then also to this angle. Now I want you to think about the distance that it's covering from here to here, okay? And then if we drew a smaller one, maybe one like this, I want you to think about the distance that that one is covering. Okay, so this is why the length of the string matters. It's covering a further distance. The longer the string is, if you were to release at the same angle, the same amplitude, it's going to cover a much larger distance than the one with a short string. Okay, and that whole time it's going to be accelerating. So at this point right here in the middle, this object is going to be moving faster than this object. So that's kind of why your angle doesn't matter there. So let's go ahead and I'll go ahead and erase this, and we'll jump into these problems here. We'll start with the couple examples, and then I'll ask you guys to pause the video, and then you'll work on the practice problems by yourself, and then you can come back and check the answers. Okay, so looking here at our first problem, a tall thin tree sways back and forth in the breeze. With a frequency of 2 hertz, what is the period of the tree? Okay, so this one's an easy one. It gives us the frequency at 2 hertz, and then it's just asking for the period. Okay, so remember our equations. We have the period of a pendulum, but don't forget that frequency is equal to 1 over period, and period is equal to 1 over frequency. Okay, so we'll go ahead and just plug this in. Period is equal to 1 divided by 2 hertz. And that is clearly equal to 0.5 seconds. That would be our period for the tree swaying back and forth. Okay. Okay, this time it says, world-renowned hypnotist Paul Bar the Great swings his watch from a 20-centimeter chain. So there's a length right there in front of subject eyes. What is the period of the swing? So we're solving for period here. It actually does this for us, but it tells us to convert the length from centimeters to meters. So we can actually just go ahead and put that on here. So length is going to be equal to 0.2 meters. We know, since we're doing period of a pendulum, remember our equation. I'll just write it out right here already. Period of a pendulum is equal to 2 pi times the square root of length over acceleration due to gravity. So we also know that the acceleration due to gravity is 10 meters per second squared. And then we are solving for the period of a pendulum. Okay. So when you plug this in, 2 pi you'll be able to plug in on your calculator, and then we're going to multiply that by the square root of 0.2 meters over 10 meters per second squared. Okay, so when you plug this into your calculator, I'm going to encourage you to do 0.2 divided by 10, hit enter. Then click the square root button and click the answer button to do the square root of that answer. Then, after you hit equals, multiply that by 2 pi in parentheses. Basically, just want to make sure that I see mistakes on this when people try to plug it all in as one equation. Plug all the numbers in and then hit equals. In terms of order of operations, you need to make sure that you don't mess that up and you have parentheses in the right spaces. So if you just do it step by step, then you can't mess it up. Okay, so if you start by doing 0.2 divided by 10, it'll come out as 0.02. Then square root that answer, and you're going to get 0.1414. Then we will multiply that by 2 pi, and you should get 0.888. So I'm going to round that to 0.89 seconds. Okay, so make sure you check your calculator, and if you're having issues with that, let me know. Let's go ahead and move on. Okay, so in this problem, it says that a spider swings in the breeze from a silk thread, so it's going to be going back and forth like a pendulum, with a period of 6 seconds. Sorry, 0.6 seconds. And then it says how long is the spider's strand of silk. So let's go ahead and write out here that the period of a pendulum, because it's going to be going back and forth, is 0.6 seconds. And then it wants to know how long is the silk strand. We also know that the acceleration due to gravity is 10 meters per second squared. So let's write out the equation for a period of a pendulum here. 2 pi times the square root of length over acceleration due to gravity. And then let's plug our numbers in. So this time we actually have the period, and we're going to need to solve for the length. Okay, so the key here is doing everything in the correct order. We want to solve for length, so eventually we have to get it out from underneath that radical, but initially we got to get rid of everything that's not underneath that radical. So that means we have to get rid of the 2 pi. And I've put the 2 pi in parentheses because it's important you keep those together. For instance, when we divide by 2 pi here on both sides, it'll cancel out on the right side, and then we need to divide by 2 pi on the left side as well. And if you don't put that 2 pi in parentheses, the way that your calculator is going to read this is 0.6 divided by 2, and then it's as if you hit enter and then it multiplies it by pi. So make sure that 2 pi is in parentheses. When you do 0.6 divided by 2 pi, you're going to get 0.095. So 0.095. And then I'm just leaving that number in my calculator. I'm not going to round it. And then that's equal to the square root of length over 10. Well, now we have to deal with the square root. So the way to get rid of that is we're going to square both sides. Okay, it's going to cancel out the square root here. So when you square 0.095, it's going to come out as 9.11. I'll go ahead and throw in a third decimal for good measure there, but I'm not rounding it in my calculator, times 10 to the negative third. Okay, so that's this side over here. And then all we're left with on the other side is just length divided by 10. Okay. Now remember that 9.119 times 10 to the negative third, that's the same as if we move the decimal 3 to the left, so it's 0.00911, okay? So at this point, all we have to do is we just need to multiply each side by 10. That will cancel out the 10 on this side. We'll multiply this side by 10. And then you will find that your length is equal to the same number. It's really just 9.119 times 10 to the negative 2, or the way to rewrite that, again, if you move the decimal point 2 to the left, it's going to be 0.091 meters. Okay? So those are our examples. At this point, I would like you to pause the video, try the exercises on your own from the document that's listed on Canvas, and then come back and check your answers. But please try the whole thing before you check your answers. Okay, so now we're looking at the practice exercises, and this is your quote-unquote homework. So it says, a metronome is a device used by many musicians to get the desired rhythm for a musical piece. If a metronome is clicking back and forth with a frequency of 0.5 hertz, what is the period of the metronome? So frequency is equal to 0.5 hertz. And then it's just asking us for the period. So since frequency and period are reciprocals, we know that period is equal to 1 over frequency. So that's going to be equal to 1 over 0.5, which is the same thing as 2 seconds in this case. So the period of this metronome is 2 seconds. Let's move on to the next page. All right, number 8 here, exercise 8. Many amusement parks feature a ride in which a giant ship swings back and forth. If the period of the ship is 8 seconds, what is the frequency? Okay, so this is just the opposite way. This time it gives us the period, and that's 8 seconds. And then it's asking us for the frequency. So we know that frequency and period are reciprocals once again. So frequency is equal to 1 over period, which is going to be 1 over 8, which is the same thing as 0.125 hertz. Okay. Let's go ahead and move on to exercise 9. It says, Tegan, a trapeze artist, swings from a 2.5 meter long trapeze high above the 3-ring circus. A, what is Tegan's period of swing? So we're calculating the period of a pendulum here. And then B, would Tegan's period of swing change if she were more massive? If so, how? It's an interesting way to word that. But let's go back through the problem and let's underline what we have. So we know that we have a 2.5 meter long trapeze, so that is the length of the pendulum, 2.5 meters. And then we know that the acceleration due to gravity is 10 meters per second squared. Period of a pendulum is equal to 2 pi times the square root of length over acceleration due to gravity. We'll go ahead and plug our numbers in. So period of a pendulum is equal to 2 pi in parentheses times the square root of 2.5 meters over 10 meters per second squared. Again, I would encourage you to do 2.5 divided by 10, get 0.25, then square root that number, and then multiply it by 2 pi, and it should come out to be 3.14 seconds. Again, if you're having issues with your calculator, please let me know. So that's the answer to A. And then for part B, I do want you to include this on your paper, so I'm just going to talk about it here, and that'll be kind of a way for me to know that you are actually watching the video and not just fast forwarding. But Tegan's period of swing, how would it change if Tegan was more massive? Meaning, like we changed the mass on a pendulum. Well, think back to our lab, and if you remember when we went from wood to aluminum to brass to plastic, it didn't matter what mass we used at the end of that pendulum, it did not change the period. So the answer to B is that the period does not change if Tegan's mass changes. So go up, make sure you write that down on your paper. And let's move on to number 10. This time it says Danielle is pushing her twin Daniel on a swing that hangs from a tree branch by 2-meter long ropes. So we have 2-meter long ropes. With what frequency will Danielle have to push Daniel as he swings? So it gives us the length of 2 meters. And then we also know that the acceleration due to gravity is 10 meters per second squared. And then it says with what frequency does Danielle have to push Daniel? Well, this is a two-step problem. In order to get frequency, we're first going to have to solve for the period of this pendulum. Once we get the period, so this will be 1, then we can solve for frequency 2 there. Okay, so we'll start off, we'll calculate the period of a pendulum. Remember, that's 2 pi times the square root of length over acceleration due to gravity. So 2 pi times the square root of 2 divided by 10. So again, please do 2 divided by 10, which is 0.2, then square root it, okay, then multiply it by 2 pi, and you're going to find out that your period for the pendulum is 2.81 seconds. So that's the first part. And then remember that, frequency is equal to 1 over period. So we'll just do 1 divided by 2.81 to get our frequency, which is going to be 0.36 hertz. Okay, let's move on. Okay, so Marla, a maid, is standing on the Vanderbilt's dining room table, dusting the chandelier. While Marla is reaching up, she slips and grabs hold of the chandelier to catch her balance. When she lets go, the chandelier begins to swing with a period of 1.6 seconds. How long is the cable connecting the chandelier to the ceiling? So this has given us period of a pendulum. That's 1.6 seconds. We know that the acceleration due to gravity is 10 meters per second squared, and then we are actually solving for the length of the chain, or the cable on the pendulum. Okay, so period of a pendulum, 2 pi times the square root of the length of the string, chain, cable, whatever, divided by the acceleration due to gravity. We'll plug in 1.6 is equal to 2 pi, please get in a habit of putting those in parentheses, times the square root of length divided by 10. Okay, so remember, we first have to get rid of 2 pi, everything outside of that radical. So we need to divide by 2 pi. These will cancel. Do that on the other side, but please do it in parentheses. Okay, remember that if you don't put it in parentheses, what's going to happen is it's going to go 1.6 divided by 2. Then it's going to multiply that answer by pi. Okay, so make sure that you do 1.6 divided by, in parentheses, 2 times pi. That should give you 0.2546. Okay, so 0.2546 is equal to the square root of length divided by 10. Okay, now we need to get rid of the square root, so we're going to square both sides. Okay, when you do this, it will cancel out the square root on the right side, and then you will get, for your answer over here, it's going to be 0.065 is equal to length divided by 10. Okay, so the last step here is to multiply by 10 on each side. Okay, and you are going to get a final answer. Length is equal to 0.65 meters. Okay, moving on to our last one, number 12 here. So on number 12, it says you've been commissioned by NASA to travel to Jupiter's innermost Galilean satellite, Io, to learn more about this volcanic moon. As you board the spacecraft, you are handed a rock tied to a 10-centimeter string and a stopwatch and are asked to derive an experiment that would allow you to determine the acceleration due to gravity on Io. So we're going to actually solve for the acceleration due to gravity. You must use both pieces of equipment and nothing more. Okay, so part A, it says describe how you would calculate Io's gravitational acceleration. So that's the acceleration due to gravity. And then B, if the pendulum swings with a period of 1.48 seconds, what is the gravitational acceleration? Okay, so the first part is discussing or describing how you're going to calculate the acceleration. If all they give you is a 10-centimeter string and a stopwatch, I'll underline that, what can we do to possibly figure this out? Okay, so for part A, I do want you to actually write this down, put it in words, and once again, that'll be a way for me to check to make sure you're not just fast forwarding through the video. So what you could do is you could take a rock and tie it to that string, and then you could create a pendulum, man-made pendulum, swing that thing back and forth, and use the stopwatch to time it. So then all you have to do is calculate the period of a pendulum there. Once you have the period of that pendulum that you've created, you can then use that and the length of the string to calculate the acceleration due to gravity on Io using that equation 2 pi times square root of length over acceleration due to gravity. Okay, so let's go ahead and move on to part B here, and it says if it swings with a period, so period of a pendulum is 1.48 seconds. We know that the length of the string is 10 centimeters, which is 0.1 meters. Okay, we are calculating acceleration due to gravity. Okay, so in this situation, it has given us the period, but if we were trying to figure this out, we would first time the period of the pendulum, take that number, and then plug it into this equation. So we'll go ahead and plug in 1.48 is equal to 2 pi times 0.1 meters over acceleration due to gravity. Okay, so we got to get rid of whatever's not under that radical. So once again, we're going to divide by 2 pi on each side. Okay, that will cancel out on the right side. And then please remember to put, when you do 1.48 divided by 2 pi, make sure that 2 and pi are in parentheses together. Otherwise, once again, it's going to do, if you don't put it in parentheses, it'll do 1.48 divided by 2, and then it will multiply that answer by pi. So this should come out to be 0.2355, and that's equal to the square root of 0.1 over the acceleration due to gravity. Okay. The next step, we need to get rid of that square root, so we'll square both sides. Okay, that will cancel out the square root on the other side. That's going to give us 0.055 is equal to 0.1 meters over the acceleration due to gravity. Okay, now it's just a matter of algebra. We need to multiply by the acceleration due to gravity to get it off of this side. We'll need to multiply by acceleration due to gravity over here. Okay, so now what we're left with is 0.055 times g is equal to 0.1. So I guess I'll just go ahead and rewrite it. So 0.055 times g is equal to 0.1. We now need to get g by itself. We need to divide by 0.055 on both sides. It'll cancel on this side. That's going to give you a value for g that is 1.802 meters per second squared. So at that point you have solved for the acceleration due to gravity on Jupiter's moon.